Hello, this video is going to be on resistance, Ohm's law, and power for electrical circuits. So first, before we do all that, we need to introduce current. So current, electrical current, has units of amperes. So this is, let's see, so current, the variable is I, and then this has units of amp. So amperes or amps, which is what you frequently call it, shortened, um, that's an SI unit. So, uh, so again, A is for amps or amperes, um, and then this is an SI unit, SI base unit. But 1 ampere, so 1 amp is equal to 1 coulomb per second, per 1 second. And what current is the amount of charge that passes through a cross-sectional area per unit time. So you can say that current here is equal to charge over a unit of an interval of time. And so this is so amount of charge through a cross-sectional area. And so what this means is that if you have, like, let's say a wire here, so you have this wire, and then you have charges that are flowing through it like this. So a cross-sectional area here would be like, let's just say you want to take a cut of this wire, and so it's like right there. So this red area would be the cross-sectional area, and through a period of time, like let's just say 1 second, um, like the charges, so so let's just say in 1 second, the charge can move this distance. Then the amount of charges that cross through this area in 1 second can be represented by all the charges in this volume right here. And so like the current through this would be all the charges in this volume. So let's just say it's like 2 coulombs. Like let's just say if each one of these dots represents a coulomb of charge, then the current here would be 2 amps because there's 2 charges that move through this cross-sectional area per second. All right. So current, again, cross-sectional charge through a cross-sectional area per second, and current, what it describes is like the rate of the flow of charges inside a wire or in a circuit. All right, now that we have current, we can go on to define resistance. So resistance here, um, so the variable is R, and resistance has units of ohms, so it should be capital too because it's named after someone. So resistance has units of ohms, and it's written as an omega, capital omega, in Greek letters. Now resistance is opposition to current, so or it's the opposition to yeah, so resistance is the opposition to the flow of charges, so opposition to current. And we can relate resistance, current, and voltage or electromotive force through an equation called Ohm's Law, which I'll get to later. But basically, the higher the resistance is, the harder it is for a current to flow given a certain voltage. Now, resistance is a property of a certain material and its geometry. So resistance is dependent on the size and shape of materials. But there's a property of materials called resistivity. So resistivity, this is written as rho. So this is the variable for it. And then units of resistivity are equal to ohms times meters. And this is a property of material. So property of material. So this is independent of the size and shape of a material. So this is a property um, related to the material itself. So, for example, copper will have a certain resistivity, or like aluminum will have a certain resistivity, independent of what size or shape it is. But depending on like the size, like a block of copper will have a certain resistance, whereas another block of copper that's a different shape will have a different resistance, or can have a different resistance. Now, these are related by the equation uh, resistance is equal to resistivity times length divided by area, where length here, so like if you have like this block of some material here, the length is going to be equal to just the like, or the length of it like this. So this is um length is going to be parallel to the direction of current. So if you want to measure the resistance of it, like where current flows um along like this path here, or so like left to right, then the length is going to be parallel to the direction of current flow. So assuming current flows along this blue line, or in the direction of this blue line, then the length is here in green, and the cross-sectional area, um, so that's what area refers to, as cross-sectional area, is going to be in red. So this is the area. And then for this, we're assuming that the shape has a constant cross-sectional area along its whole length. And so area here is going to be normal to, or perpendicular to, or orthogonal to, it doesn't matter what you call it, to the direction of current flow. And so resistance here, so the resistance of this block is dependent on the resistivity, the length, and the area. And looking at proportions, we know that the resistance is going to be proportional to resistivity. So the higher the resistivity is for a material, the higher the resistance is given the same dimensions. Resistance is also proportional to, resistance is proportional to length. So the longer it is given the same area and resistivity, the more resistance it's going to have. And then resistance is inversely proportional to cross-sectional area. And so the larger the area is given the same length and resistivity, the less resistance it's going to have. And this makes sense if you think of this like, for example, if you think of electrical current, a common analogy is for flow of water in water pipes. So if you have a bigger pipe, then it's going to there's going to be less resistance for water to flow through it. Whereas if you have a longer length of pipe, there's going to be more resistance because the water has to flow through a longer length of pipe, and there's more chance for it to like slow down because of the pipe. And then resistivity is, so that's harder to explain without, but like if you have a more viscous fluid, I guess that can be like an analogy for higher resistivity, then it's going to be harder to flow through pipes. And so these are proportional. So if you remember this, then it's easy to derive this relation here. Now, resistance can also depend on temperature for material. And so if you draw a graph of resistance versus temperature for a certain material here, then for metals, or conductors. So this is for, we're going to focus on conductors. But for conductors, it'll look something like this. So this is low, or so these are extremely low temperatures. So around absolute zero. Around absolute zero, most conductors will act like superconductors or have really close to zero resistance. And you can have zero resistance if you get to absolute zero, but then there's like impurities in the metal, or things like that can affect it. But at extremely low temperatures, you'll have around zero resistance. And then as it increases, as temperature increases, you get to a linear region. So this is so at normal temperatures, or at like temperatures that you would usually encounter, resistance increases linearly with temperature for conductors. And so we can write this as, so resistance is going to be equal to some R0, this is like a reference resistance, times 1 plus alpha. So this is a temperature coefficient for resistance, times T minus T0. And so here R0 and then T0 are like reference temperatures and resistance. So R0 is resistance at T0, and T0 is going to be our reference temperature. So this is reference temperature. So what this is saying is, you can see this is kind of like a point slope form for an equation. If you know the resistance here, so let's just say that this is T0 and this is R0, then the resistance, you can find the resistance along this linear region by knowing this alpha coefficient. So this is alpha, Greek letter alpha, temperature coefficient for resistance. And so another way you can write this equation is the change in resistance divided by this reference resistance is equal to alpha times the change in temperature. So alpha is like the slope of this, and alpha is dependent on the initial temperature and resistance. So it's dependent on the reference temperature. So for different reference temperatures, the alpha value will change. But what this is saying, what these equations are saying, and their equivalent, are that if you increase or if you change the temperature, then the resistance will change linearly according to this alpha coefficient. So resistance is dependent on temperature here, and for conductors, it'll increase linearly with the change in temperature. And it's also dependent on the geometry and property of the material it's made out of. So for a resistor, the resistance will depend on the cross-sectional area, the length of it, the resistivity of the material, and the temperature it is at. Now we can relate resistance, voltage, and current through Ohm's law. So Ohm's law is an extremely important equation in circuit analysis, and it states that so Ohm's law here is that voltage is equal to current times resistance, and you can rearrange this in multiple different ways. But this relates voltage and current through resistance. So for a given voltage, the amount of current through material is dependent on the resistance. And we can see here that if we draw, so Ohm's law, Ohm's law is obeyed for ohmic materials. So ohmic material. So if you have an ohmic material, such as a resistor, what Ohm's law says is that if you have a graph of voltage and current, the graph will be a straight line. So as you increase voltage here, the amount of current that flows also increases proportional to voltage. We can see that this is true because you can rearrange this to be current is equal to voltage divided by resistance, where this is the slope here. So 1 over r is the slope of this graph. And if a material obeys Ohm's law, then we can see that since resistance is constant for the material, this will be a straight line. And so voltage here, as voltage increases, current increases proportionally. That's what Ohm's law is saying. Now, not all materials obey Ohm's law, and so not all materials are ohmic. And so if we have a non-ohmic material, then what that looks like is, so what this looks like, for example, a diode, which is based on semiconductors, is if you have a graph here of voltage and current, it's not going to be a straight line. So for diodes, this graph will look something like this. So this should be at 0. But like for a diode, which you can, it's a so this is a semiconductor based circuit component, and basically it should only allow current to flow in one way, but what I draw here is similar to an ideal diode. But for a diode, at small voltages, there's almost no current flow, and then suddenly the current flow increases really fast. And so same thing in the negative direction. But this obviously isn't a straight line, and so this isn't an ohmic material. It doesn't follow Ohm's law. But if you have an ohmic material, such as normal resistors or wires or standard materials, usually that if there aren't semiconductors, so for normal conductors or resistors, they'll follow Ohm's law, and so the graph of voltage and resistance will be a straight line. Now, Ohm's law, Ohm's law is important because you can use Ohm's law to analyze circuits really easily. So you can apply Ohm's law. So like if you have a circuit with a resistor or multiple resistors and like even multiple voltage sources, you can use Ohm's law to find the voltage, current, and resistance across each component of the circuit. And I will probably cover that in a later video. But another important concept is power. So the power through an electric circuit or through a component. So power, we already know power has variable P, and then the units for power are going to be in watts. So this is not watts, and then this is equivalent to joules per second, or change in energy per second. So power is equal to the change in energy per change in time, or work over change in time, or per unit or interval of time. So how do we get power in circuits? Well, we know that power being equal to change in energy over an interval of time, we know that current here, current is equal to charge over a unit of time, and then voltage is equal to energy per unit charge, or per charge. So we see that these charges cancel out, and then this is equal to power. So this is equal to current. and this is equal to voltage. So we get that power is equal to current times voltage. Now, one important thing to note is that this doesn't necessarily mean the area under a current voltage graph. So, like for this graph here, we see that if we were to find the area of it, it would have units of current times volt, so it would have the same units as power, but the area would be 1/2 IV, whereas power is just IV, or current times voltage. So the area of this graph, underneath this graph, is not the same as, it's not power directly. And so that's not true necessarily for, like, you can have a graph that shows with current and voltage that has an area with power, but like for this graph where it shows the voltage and current across, like, so for a material like this where it's like if you increase voltage, current increases, the area of this graph isn't power, or isn't directly power. It's power. It has a coefficient of 1/2 in front of it, and so you would have to multiply the area by 2 to get power in this case. And so yeah, like it's related to power, but you can't calculate power just by the area of the graph. You would have to multiply it by a coefficient, and so that's something to be careful of. Again, like I said, it has the same units of power, and you can find power through area, but it's not equal to the area. It's related to the area through a coefficient. And now, one thing about this is, from Ohm's law, we know that current is equal to voltage divided by resistance, and we know that voltage is equal to current times resistance. So substituting in, we get that power is equal to current times voltage, which is also equal to, if you substitute for current, then it's equal to voltage squared divided by resistance, which is equal to, if you substitute instead for voltage, current squared times resistance. So these are all valid equations for power. And in order to calculate for any one of these variables, you only need to know you only need to know two of current. So the variables you can have are power, voltage, current, and current is current and resistance. You only need to know two of those to calculate for the last two. So if you're given voltage and current, you can calculate power and you can calculate resistance. Or if you're given power and resistance, you can calculate for voltage and current. And so those are all related. Now, with these equations here, so you have Ohm's law. I'll recap. Ohm's law is voltage is equal to current times resistance. Power is equal to voltage times current. And then you have resistance here is equal to resistivity times length divided by cross-sectional area. And then you also have resistance is equal to a reference resistance times 1 plus this resistance temperature coefficient times a temperature minus the reference temperature. Now, when you're analyzing circuits, usually you only have to use these two equations. And then when you want to find out the resistance of a material, or like a certain geometry of material, then you can use these two equations. So usually you won't have to use the bottom two equations to analyze circuits themselves. Usually you can just use the top two for circuit analysis, but the bottom two are for properties of resistors themselves. And so that concludes the video on resistance, Ohm's law, and power.